In this video, we're going to go through two different ways of determining whether data that's given is an outlier. So I've sort of written out the methods here, but what you want to do is you want to take the upper quartile. You want to also find the interquartile range, which, by the way, just as a reminder, is the upper quartile take away the lower quartile. And adding 1.5 lots of the interquartile range onto the upper quartile gives you the sort of maximum limit. If that data is larger than that maximum limit, then that data counts as an outlier. In the same way that if the data is so extreme that it's less than the lower quartile minus 1.5 interquartile range, it's also an outlier. Going on to the other type, before we have a go at applying it, we have to first find the mean, which we'll do using a formula, and we'll also find the standard deviation using a formula. If the data is larger than 3 standard deviations onto the mean, then it's an outlier, and if it's less than 3 standard deviations below the mean, then it's also an outlier. So let's have a go at using it. Just before we do, it says use your knowledge of the large data set to explain why it is unlikely that this is a random sample. The trick to this one is realizing that, well, a sample of 12 days is taken from May to June. May and June is in the summer. What do you expect in the summer? We don't expect there to be rain. However, every day that a sample was taken, there happened to be rain. So the fact that there was rain every day in the summer suggests that the sample was probably only taken on rainy days in the summer. So you can see something like there was rain every day in summer, which doesn't make sense. Great. This data is also summarized with the lower quartile Q1 being 1.35, median being 3.1, and the upper quartile being 4.65. How do we determine whether there's any outliers? Well, we take the upper quartile, which is 4.65, we add onto it 1.5 lots of the interquartile range. The interquartile range is the upper quartile take away the lower quartile. That's 4.65 take away 1.35. If you put all of that into your calculator, which I'm just going to quickly do, that's 1.5 lots of 65 take away 1.35. You get a value of 9.6. That's a 3, by the way, sorry about that. 9.6. What that means is that if the data is larger than 9.6, according to this, then it's an outlier. Is there any data larger than 9.6 in the rainfall column? No. So there is no outliers in the upper end of the spectrum. Let's now look at the lower end of the spectrum, which I'm just going to change color for. So what we do there is similar. We take the lower quartile, 1.35, and we take away from it 1.5 lots of the interquartile range. Again, the interquartile range is the upper quartile, take away the lower quartile. So 4.65, take away 1.35. You put all of that into your calculator, which again, I'm just going to quickly do. 4.65. You can skip a few seconds to see the answer. That gives you a value of minus 3.6. So that means that if the data is less than minus 3.6, which in this case in the rainfall column, there's no data that's less than minus 3.6, then it would be an outlier. So in this case, are there any outliers? No, there's no outliers. If we did have a rainfall of, let's say, 11 centimeters one day, that's larger than our maximum limit, 9.6. So because the data 11 is larger than 9.6, we'd say that data is an outlier. Hopefully that makes sense. Let's go through the other way of finding an outlier. So the other way, what you first need to do is find the mean and standard deviation. By the way, the method that you use is completely up to you, but it really depends on the question. If it's easier to find the mean and standard deviation, then you can use this method. If it's already given you the quartiles, or it's given you a graph where you can use to find the quartiles and medians, then it's better to use this method. So I'm just going to write down these two formulas that are given to you in an exam. I'll explain what they are. So the mean is the sum of all the terms, in this case the sum of all the weights, divided by how many weights are being measured. That's 1, 2, 3, 4, 7. So we can do 5.7 plus 6.8. So we're finding the sum of all the individual weights, in this case because x represents weight. 6.8 plus all the different weights all the way up to 8.3. And then you divide by how many weights there are. So in this case there's 7 weights. That'll give you your mean. So I'm just going to quickly do that. You can skip ahead 10 seconds if you like. .9 plus 8.3 all divided by 7 gives you a value of 7.4. Now that we've got the mean, we need to find the standard deviation so that we can multiply it by 3. To find the standard deviation, let's break this down. The first thing to know is that sum of x over n is just this mean that we found. So we're taking away 7.4 all squared because we're taking away the mean squared. The sum of x squared, what this means is that you take the squares of each individual value that's recorded. For example, let's write this out here. The weight of 5.7 that's recorded, you take the square of that. And then the sum means you add it onto the squares of all the other terms. So plus 6.8 squared plus 9.4 squared plus the square of all the other terms all the way up to 8.3 squared. And then once again, you divide by how many terms there are. So there's 7 terms. So I'm just going to quickly do that on my calculator. Sorry, I didn't really get time to do the calculations beforehand. Again, you can skip 10 seconds if you'd like. Almost there. Yeah. And you get a value, by the way, I've divided by n, which is where the divide by 7 comes from, because that matches this part of the formula. That gives you a value of 56.45, and because that's all of this in general that I put into the calculator, we can just put all of that here. In which case, you can now put square root of 56.45, take away 7.4 all squared. 4 all squared, and that's equal to a value of 1.3. Let's now find the mean plus 3 lots of standard deviations and mean minus 3 lots of standard deviations. So the mean is 7.4, and if you add 3 lots of the standard deviation that we found, 1.3, that will be 7.4 plus 3.9, which is equal to, let's do the working out, and that's equal to 11.3. So what that means is that if the data is more than 11.3, is there any data more than 11.3? No, there isn't. But if there was, then that data would be an outlier because it's so extreme that it doesn't fit in the trend with the rest of the data. Lastly, I'm just going to change pen color because there's quite a lot of writing going on in this page. But mean take away 3 lots of standard deviation is, well, the mean value of 7.4. Take away, sorry, my writing is quite small. I'm just going to do it here. The mean value of 7.4. Take away 3 lots of the standard deviation, which again is 1.3 that we found. This is value here. 3 lots of 1.3 again is 3.9. 7.4 take away 3.9. That's 3.5. So what this means is that if any piece of data, is less than 3.5, that data would count as an outlier. Is there any data less than 3.5? No, there isn't. So in both cases here, there are no outliers, but hopefully you get what I mean in terms of when they appear. If you like this video, be sure to leave it a like and subscribe. I'll post more content like this very soon. Thanks for watching.